Thank you all. Just gonna take my notes here. Okay. Hi. Glad to see you all. It's been great, right? It's first day. It's actually the only day, right? Cool. Yeah. Yeah. Can you hear me better this way? Okay. Cool. Oh, just one thing before I forget. For the questions, there's a mic here, so just pick it up. I'll forget it. So, yeah. Cool. So Noir, I won't get your money back. Sorry. That's that's it. There's here. It says that I won't do it. So Noir, let's just go on our rundown, and then let's talk a little bit about Noir and everything else. So let's talk about ZK. I think this part is pretty. Everyone should be comfortable with this. Then we're going to talk about Noir and why is Noir, mostly why, before the how. And then we're going to talk about our project. So, yeah, just a small thing you could follow along. You can follow along if you have your laptops. Otherwise, just, don't. And then, let's finally hack something and try it. So we know that ZK proofs are powerful. I think everyone knows that if you're here. But with great power, usually come univariate polynomial commitments. And if you're like me and you struggle with this kind of math, then maybe Noir is exactly what you're looking for. We need these kind of usable ZK DSLs you can write just as the same way as you write a normal program. So obviously I'm kind of excluding everyone that doesn't know how to code, but still I'm including everyone who knows how to code but don't have the time to understand the math behind it. So we had to copy, basically, we decided to copy a syntax of a nice language, and Rust is a nice language. So we're like, okay, let's do Rust, and that's basically how it started. So if you try to find the difference between one and the other, probably the Noir one is going to be a little bit simpler, but they still have the same syntax. They look very similar, but again, it's just a syntax. Once you start scratching the surface, it's going to be very, very different the way it works. And I'm going to show you why. So if you try to spot the difference between these two images, that's kind of on me, right? Because I have the two different colors, so I can guess that one is Noir and another one is Rust. But as you can see, apart from small things like assertions, for example, those are things that you only get in Noir. Everything else is just the same. So we want to write code instead of write circuits. Circuits is basically, if you've been here for a while, maybe you wrote your circuit, you draw your circuits and then connect the wires, etc. And that's nice, but it's kind of a different paradigm. We want something that developers are used to work with: code, programs, smart contracts for Aztec Sandbox. So so we want to target not only like the beginners, but also everyone else that just I just want ECDSA signature verification. I don't really know. I don't want to implement the whole thing. Just give me a module I can use so I can develop further. And so we kind of want to target everyone, not just the beginners. And actually, we have like big projects being built on Noir, and they are just fine. And so it's not just for pros; it's for everyone. So our build plan. So basically, I'm gonna have like 3 or 4 chapters. Let's see how much time do we have for all of that. So basically, I'm gonna just introduce Nargo. So you see Cargo, Nargo. It's like a package manager. You can use that to init a project and etc. Then I'm gonna go over the Noir syntax, just very basic things. You can always go on to the docs and learn more. I'm gonna write some tests. I think tests are there already. Yeah, and then just how to generate and verify proofs. And then the standard library, it just we're just gonna go over maybe 1 or 2 examples of the standard library. How can you use it, and maybe like using another libraries. And then the good stuff, which is basically the browser. How can you have proofs running on a browser? So yeah, literally on your machine or in a mobile phone or something, and yeah, and then maybe a surprise. Let's see. Yeah, it'll be a cool one. Yeah, I'm gonna leave out the verifying proofs on chain because it just everyone knows how to deploy a smart contract, I guess. And if you don't, that's okay. Just talk to me later. I'll help you. But yeah, I'm gonna leave this out because it takes a lot of time, and yeah, it just yeah, it's kind of difficult. So yeah, finally, I think let's start. So I have here my 3 QR codes. I guess the most important is the latest one if you're following with your laptop because it has some resources. Yeah, there's also the Noir docs, which have everything that you're going to be using today. And also my limo, what's it called? Yeah, it's kind of a link tree, a Web3 link tree. You can, there's all my profiles and etc. if you want to follow me. Okay, no phones in the air. I promise I'm not gonna pick a gun, like a t-shirt gun, and shoot. Promise. So you can put your phones on the air. No. Okay, sorry, still phones in the air. Phones in the air. Okay, cool. So yeah, if you didn't pick it up, just tell me. It's a GitHub repo, so it's no big deal. Yeah, it's this one, Noir in an afternoon. So noirlang / noir in an afternoon, and there we get it. Cool. So let's start. So here's I was working on the cheats, cheat codes. So let's start with something. This is the repo. I'm just gonna basically install Noir app. So if you're used to using like Foundry app or Rust app, it's basically like a nice tool you can run and basically get Nargo there, and then you have all the tooling you need to start developing on Noir. So basically you go to that repo, and if you have the README, you can basically go and copy this line and run it. I'm not going to run it because I did it already. But yeah, we're going to have this tool, Noir app. And this is really cool tool. You can basically use it to install different versions, branches, PRs, commits, repo, everything. It's really a nice tool. So if you have it already, or better yet, if you don't have it already, just let me know. Okay, cool. I assume everyone has gone through this. Then you can install Nargo. So basically, if you're finished that, maybe you need to like restart your terminal because of the path needs to be there. But you should get Nargo version, and you should get some kind of version. Sorry, you would need to install Noir app first. So you go to Noir app, and I'm gonna tell you to install the version 0.11. Okay, I'm gonna say this one because it's a bit faster, but it's not stable yet. But it's cool. I tried it, trust me, bro. So you can install 0.11. If you do noir up n, it will install the nightly, which is 0.12. And yeah, I haven't tested that one, so it's cool to use 0.11. And it could take a little bit because of the SRS, which is basically the ceremony that we did in 2019. Yeah, it's needed for our circuits. So at the end of that, you should have Nargo, and you should get 0.11. Any issues so far? Okay, yeah. Okay, I think I can go. Yeah, I can move on, and then you'll definitely catch up because this part is really easy. So it's basically just starting a new project. So I can go. There's basically two very similar commands. One is new, that will start in a new directory. Init is going to start in the current directory. I'm saying this because I also don't remember which one is the. So ZK Summit. So it will create a new project, ZK Summit here, with a folder and a file here, basically two files actually. And this is a basic circuit, I guess the most basic circuit, which is. Is there any way for you to zoom in a little bit? Yes, definitely.
Maybe we also turn off the lights because it's a little bit.
Is it cool like this? Yeah, the lights.
Much better. Can we turn off the light? Is everyone okay with that?
There are lights, maybe. Thanks. So this is a very basic circuit. You have basically the FN syntax, just like Rust, when you define a function. You need to have a main function in a Noir circuit, not in the ASTIC contracts. That's a different thing. There you don't have a main function. Here you have a main function because that's what you're going to actually run. And then you have like the variable syntax. It's just like Rust. Except you have this little thing called field. So those of you that know cryptography, especially those who understand it more than me, which is not difficult, you have this. You can treat this as kind of some sort of, oh, cool. You can treat it as some sort of like big integer or something. You can make some arithmetic with it, but for example, you can't use it for comparisons. So yeah, we still can use like uints. But for this example, just go with field. If you want to define like an array, just like in Rust, you go and say how many fields you have in that array. This needs to be known at compile time, the size of an array, just like with every ZK language, I think. There's this public keyword, so we kind of think that privacy is the norm, so it's normal to have privacy. So you only say what's public. That makes sense. It's like, so basically, once you give this to a verifier, the verifier will only know the value of y. Value of x is kept only to you. Only you know this. You want to prove that. And then we have addition, subtraction, multiplication, etc. So you can have like let z equals to x plus y. You have like shorthand operators. So if I make like this, if I can make this mutable, I can go and say z plus equal 1, for example. That this is okay as well. So we have these kind of shorthand operators. Then we have like for loops. You can go and say for let I, for I in, oh, thanks GitHub. You can make for loops here. You can have if-else conditions. Like if I say like if x, I can say x. Oh yes, I can. I can say like if x equals 1, I can do something. Otherwise, just do something else. Again, it's like basic control flow stuff that we are used to work with. And then we have this assert keyword, which is basically if you want to prove something, you need to prove some assertion. You need to make some, need to assert something. You're going to say, yes, this only verifies if this is true. And so this will only verify if X is different from Y. And so that's the assert keyword. It's basically putting a constraint into your program. And then another thing that's really cool that we can have is structs. And so you can have like struct person, for example. Okay. So one example, it's like you are Brad Pitt and you are the owner of a fight club, and so you want to prove that someone knows the password to enter the fight club and has like the minimum required age, and yeah, but you don't want people to tell you their age or the password. So, for example, you could have like a struct and say like a person that has a certain age, and say age is it's a field as well. And so then you can also like declare globals and say global minimum age, and say global minimum age is going to be 18. And so yeah, basically you can have like age, you can have a password that's also only known to whoever is saying the password. And then you have like password hash, for example, password hash. That's going to be the password that, like the hash of the password. Everyone knows that. That's okay because it's hashed. So, so in our example, yeah, someone could prove that they can enter your fight club and fight to death. Then basically, yeah, another thing that's really interesting and I should mention is the return value. So if you say, let's say that this circuit returns something, you do it just like in Rust, but when you pass it to your program, when you use it, you basically have to pass it as an input, because just basically what it says is it's just like it works like if I would say return here, it's going to be also a public field, and so, and then just at the end of whatever calculations you're making, and then it'll say, yeah, just assert that return is equal to whatever you did. But this is not so cool. So the guys with Noir team basically just implemented this nice return. And that's why it needs to be public, because you're actually passing it when you verify the circuit. And so, yeah, that's just one of the questions that we have sometime. Why does the return value need to be public? That's the reason. So you need to pass it when you verify your circuits. Cool. So for tests, we actually have now like tests failing, but I'm not sure if that's in 0.11. I'm not sure. So yeah, but basically you're gonna have or you have already tests that are supposed to fail, which is cool, and we didn't have that for some time. And so let's forget about the password part and just remove this, and let's just assert that age is it's bigger than the minimum age. Sorry. Sorry, not age. I'll just actually pass a person and say, yeah, person. So it's a fighter. Fighter is a person, and let's say that person fighter age is bigger than the minimum age, and yeah, basically now I just go and instantiate the person and say let's Brad Pitt. It was Brad Pitt, right? That did it. Yeah, that's true. Okay, so yeah, 55. Okay, I guess GitHub knows that Brad Pitt is it 55? Is he? I don't know. He looks younger though. 59. Yeah. Okay, so now I'm just passing this to this person basically to my circuit, and this should hopefully pass. Let's say. So the way you ran, okay, it's already complaining about something. Comparison value. Oh, okay. It needs to be an integer. As you wait, for example, and like as you wait, and yeah, yeah. Just casting these two integers. The way you run it, just go nargo test. Okay, I need to ZK submit nargo test, and it passed. So it seems like, yeah, Brad Pitt is allowed to fight. But if he was 5 years old, which he was at some point, it will fail. They say, yeah, it failed. It just the constraint failed. Now you ask me, just like, okay, it's cool, but sorry, I need to unlock this. And yeah, but you're not actually proving something. You're just checking that the syntax is correct. That's true. That's what the test does. If you need to do something else, then you actually need to prove something. And let's go over that. So first of all, we need to basically create the files that will go and generate the proof and verify. So I'm gonna go and say nargo check, and that will generate my prover and the verifier. You see that verifier knows nothing. It's like Jon Snow knows nothing. But here, like in the prover knows the age. So prover is hopefully Brad Pitt and his passport, and verifier is whoever is controlling the border or whatever, entrance to the Fight Club. And so here you have it. So you just go and put your data in the prover, say 59, right? 59, and go say nargo proof, and it will go and generate the proof and say, yeah, here is it. Here's our proof. Yeah, it's kind of difficult to read, but it's a proof. It's kind of small as well, which is what we want. Just narc. If I put something it's not valid, like 5, it will just fail to actually create the proof itself. It cannot satisfy constraint. So I have the proof here, and I want to verify that. So just go and run nargo verify. So you see that it's very straightforward. There's no math here. There's no difficult steps here. Just running nargo commands and writing Rust. Right? Oh, yes, there's a question here.
Yeah, so here it's basically a separate file you write a prover, like you write the witnesses and the prover holds. And you put fighter in brackets. So fighter was...
It's because it's a struct. Yeah.
It was a specific instance of the structure.
Yes.
And basically the syntax is you put that specific instance between those square brackets and you put it. In that prover function, let's say we had fighter 1 and fighter 2. Could I have put in the same file the 2 instances?
Yes.
Basically pick one by some control statement.
Yeah. Yes. Actually, the circuit will go and use both, and then just choose the branch that's useful. So yeah, you could do like fighter 2, and say like the age of the fighter 2, which is 50, 60, and then you can have like here fighter 2. I don't know if this is what you were asking, and then you can like have the control flow, choose what branch do you want to, but there's no way of just passing like yeah, it needs to be known at compile time, like the size of, yeah, how many arguments you're passing, etc. Yeah. Cool. So as you've seen, like this is it. This is Noir. Okay. Thank you. Yeah, just I'm kidding. There's more to it. Sorry. Yeah.
Is it normal that nargo proof takes forever? Does it seem like it's doing anything, or like?
Yeah, I mean, it takes a while. I think part of it is not only creating the proof itself; it needs to create the witnesses as well. And so, yeah, there could be parts of that are not as optimized. But I guess you're going to be surprised when I show the browser, which is exactly the same example. Oh no, it's a similar simple example, and you're going to be surprised how fast it is actually. So yeah, but you should definitely not like use an argo proof for benchmarks. Yeah, you should basically get in the Noir file and then compile it and then feed that to a backend like Rotzenberg, for example, and then you can make some benchmarks on that. Yeah, because an argo proof, I mean, it's just a CLI tool. It's meant to be easy to run, not like the fastest thing. Cool. So I said that there was more to it, and of course there is, because otherwise we'll be kind of constrained with how many things do we have. And so if you go to noirlang.org, you're gonna see. I'm gonna make this a little bit bigger as well. You're gonna see basically the docs. I'm gonna choose the dev version. I know this is about 11. I don't even know. But here you have like Nargo, everything I said basically, and also how to generate a solid verifier. It's very easy. And then you have like all the language concepts that I've just introduced: fields, integers, boolean strings, arrays. You can console log stuff. You can use references like REST references. You can use vectors to resize arrays, and yeah, it's really cool. And logical, yeah, and there's also unconstrained functions, which is, yeah, it's another talk, but it's really cool if you want to explore unconstrained functions as well. Yes, so and then there's this thing called Noir standard library. So if you're used to use like low-level languages, you know that there is a standard library that can optionally import or not. And in this case, it's kind of the same thing. We have some primitives that we can use, and you can use out of the box when you use Noir. For example, hash methods. You have like a bunch of hash methods. Some are better than the others for whatever reasons you're using them. And then, yeah, scalar multiplication. Another one that's really cool. It's ECS asynchronous verification. Yeah, Merkle trees, stuff like that. And so we're going to use this because we want to prove that Brad Pitt, yeah, knows the password as well. Not only has the age, but also knows the password. So, regarding benchmarks, one thing you can do is just go and say nargo info and get the number of the gates. And I'm gonna go on a side quest here to explain what is this thing is here. So basically, Noir is just a language. As I said, it's just a shell. You compile Nargo to compile Noir circuits to this intermediate representation, which is ACE here, and that's going to be fed into your backend. And so you're going to see that this only has 19 opcodes and 2K, almost 3K gates, and basically you can use that to benchmark and try to at least compare circuits within the same backend. So for the password, let's use Poseidon. I guess it's a nice function for ZK. So just copy this basically and say just put it here so I don't forget. And so for the fighter person, and then I'm gonna just say password and password. It's a field, yeah. Does it expect a field? It's a field. Yeah, it's a field. A field, password, and password hash. This is public. So for that, we need to basically calculate what's the password hash beforehand. So if you don't trust me, you can basically run this script, and you're gonna have like the hash that you need, and you're gonna confirm that the thing that I've put in the README here, it's actually true. And so let's say that this is 1, 2, and this is the hash of 1, 2. So just gonna go on my prover, actually on my test, and say this is my password 1, 2. Not a great password, to be honest. and then the password hash. And finally, I'm going to assert that, so not need to calculate the hash and say, just like this, actually, yeah, just hash plus I, then this is the curve, and yeah, hash 2 because it's 2, and then you just go and let's assert. Thank you, GitHub. One thing that's missing, you need to import the standard library. Use dep std. Okay, cool. Those of you following along, I've written a lot, so let me know when. That's it. So cool.
Shouldn't you change this one to the password on the line 11?
Line 11, sorry.
Yeah, at the end, the hash, the brackets 1, 2, so it's a constant. No?
Yeah, that's true. Yeah, you're right. It's a password. Yeah. Thank you. So if you run this, yeah, it's 1, 2. Oh, it's sorry. It's an array. Okay, cool. So if I run this, I'm gonna run an argo test, and yeah, it passed. Cool. So yeah, should I try to make it fail? I'll try to make it fail.
Does the fancy run test syntax work?
Sorry?
Does the fancy run test syntax work?
Yeah, I can try. I remember it was like should fail, something like that. So it was like tests should fail, I think.
Oh, no, I meant when you click it in VS Code.
Oh, this one. Yeah, it should work. Okay, sorry, it fails because of the test should fail. Yeah, so yeah, that's cool. Thank you for pointing this. I'm already used to have this, and also for compiling and executing, there's this handy VS Code extension for Noir that you can use. Yeah, thank you. Yeah, there's the syntax should fail, and basically you can have tests that expect to fail. Cool. So let's go basically create this proof. Gonna put that. It's already in the README in a nice TOML format. So I'm gonna put it on my prover file and say this is password. This is password hash. So I can go and say in argo proof. Expected environment password. Okay, seems all right. I don't know what I'm doing wrong. Maybe
Maybe it's expecting a different TOML syntax for your array.
no. I think this is correct. Well, I'm just gonna remove like the struct itself and say age, maybe. Field, this is age. There. Okay, yeah, because of the test. Okay, cool. So I have my proof here. So again, let's just go and run Argo info just to check how much this hash cost us. And yeah, it kind of costs a lot of AC opcodes, but the backend circuit size actually is not too big. It's 5K for Poseidon. So yeah, let's not try Kachak, but you can check it. It's obviously it takes actually less AC opcodes, but the backend size kind of it's much bigger. Yeah, you can just do the same way. I actually have an example here. I just want to save the time for other stuff. So then you have, let's say that you want, okay, I want another dependency. I want STL standard library is cool, but I want something else. That's okay. You can go on your Nargo toml and just put it here in dependencies. So ZK sync. Oh, okay, not ZK sync, but I like AC recover library, which is one of the first, I guess. And you can say basically just put your tag here. Just copy here from my notes. You can say it like the GitHub, whatever. So EC recover, Noir, just this one. Just paste it here, and then I think that's it. I'm not sure if I need to put the directory. Anyway, let's try. And yeah, basically you can import EC recover library just the same way as you did with the standard library. You go say use dependency and then EC recover. EC recover is basically, it mimics the Ethereum recover function. Basically get an address from ECDSX signature. Yeah, this is a nice little library that I like to use. So in this case, let's not just. I think I made my point on this. Cool. So you tell me, and now what? Right? Should I pass to? I mean, what? How does this help me? And I can tell you can put that on a solidity verifier. You can generate a solidity verifier from a Nargo from a Noir circuit. So you can go and say Nargo code gen verify, and let's just wait for it. Okay, and here is it. It's just it's a smart contract, which was written by very smart people, and which I don't understand anything that's here, but yeah, it just stores verification key and the hash, and basically you can use it to verify. So you can go and just check the verify function and say exactly what does it expect to get, and you can deploy this contract. You can wrap this contract into your own contract, and like with just use it in your regular Web3 flow on Ethereum or whatever EVM you're using. And then there's the cool stuff, which is, I mean, I like it. It's cool stuff, not. Okay, yes, question?
How much gas verification costs of this specific?
I'm going to say a lot because I don't know the exact, but I think 400K?
Yeah, it's not okay.
Yeah, I think it's a bit more than the turbo verifier, but it's faster.
How many? 400?
Sorry? 400K. Yeah, it's not cheap. Yeah.
But it's roughly constant, right? Regardless of the size.
Yeah, it's constant. Yeah. Yeah. That's.
How it increases every single new public parameter that you have?
Yeah. I mean.
Any measures?
Yeah. I mean, it will increase. Yeah. With
So you have this byte-32 code data public inputs.
Mm-hmm.
If you add more public inputs, how will it increase?
I mean.
It's like 500 something gas per public input. It's the majority of the actual cost is cool data. It's like 100 gas a copy. And then that's a cool data cost per public input. 150 gas.
Yeah.
What is the outlook? Is it going to be 400 or some optimizations?
No, it's going to be about 400. Yeah, if you 400K if you deploy it now. Yeah. Yeah, with optimizations, I mean, you need to optimize. You need to compile this in an optimized way. I think with some rounds of optimization, I've been using 5,000. Sorry.
Entirely optimized. Does the gas costs work out really drop voltage? The gas costs aren't going to drop voltage.
Yeah.
Pretty tightly optimized.
Yeah, it's also going to complain that verify is not used, and that's because it's the function signature that's being used, and so some compilers will complain and say, yeah, you're not using this, you're just calling the function signature directly. So most of it is actually assembly. So cool. Now the cool stuff. So let's say that you have a browser, and what I want is this. I want basically on the browser. I want to prove that X and Y are different. And yeah, just a very basic circuit. And this is like the end goal that we want to arrive here. Just go and calculate, verify off chain. I'm also verifying on chain because I have I think it's on Mumbai. So yeah, you basically, this is what we want for this example. Yeah, this should fail actually, but it's spinning. I need to fix this. Yeah, but this is our end goal. So let's go over a little bit of the code. Here's this browser thing. And so it's a Next.js. So it's there's a lot of boilerplate. That's why I put it here. And there's a page, just one page, very basic. And here is like the main component. So if you're used to React, you're gonna find it useful. If you're not, that's okay. It's JavaScript basically. And yeah, basically what you're gonna do is just some person is gonna input whatever values they want. They are gonna calculate the proof, and calculate proof will go on this class that we're gonna try to implement. And that's it. Basically, the class is here, Noir, and our goal here is basically to create this class. Actually, I'm not gonna write. I'm just gonna copy it from the sheets here. This is basically just the Noir starter example that I shown in the beginning. But I removed a lot of things just to make it easier. And so yeah, basically just go over like the imports so I can clarify something. So you see, the first one is like flat. You need to install flat because yeah, there's some inconsistency where the Bratenberg expects a non-compressed circuit, but the CVM, I'm going to explain what that is, expects a compressed circuit, so we need to decompress it. And then we have like the actual backend, the CVM stuff that we're going to need, and then ethers because I'm lazy, and then some type because it's TypeScript and they're going to complain if I don't import this. And so before, what is this ACVM thing about? So remember that when I said that when you compile Noir into something, it will compile into ACIR, abstract circuit intermediate representation. That you're going to feed that into this ACVM, which is abstract circuit virtual machine, I believe. Yeah, and that will basically translate your ACIR into whatever your backend is looking for. In our case, our backend that we like to use is Bratenberg, and so that's why I'm importing like these three pieces. Basically, I'm importing the ACVM because I'm reading directly from the ACIR, and I'm importing the backend, which is here, Bratenberg. One thing I didn't say is like, in this case, you're expected to already have your circuit compiled. We are actually gonna, we're working on Noir WASM, which will basically compile on the fly as well. But for now, you just compile with an Argo compile, and it will generate this nice file that you can import. It's just a JSON, and so yeah, that's it. So I'm gonna go back to my sheets and say, it's a class, so I'm gonna just go until the init, and let's talk about it. So I made it a class, but you can just use it separately. So basically, I'm passing already the circuit, like the compile circuit, in my web page, and then I need to init this init Noir. So the ACVM, you need to init for the browser, not for the node. So if you're gonna see like the Noir starter, there's actually a conditional on whether it's on the browser or not. And then I'm gonna import like the byte code from my circuit, the compile circuit. I'm gonna decompress it because I'm gonna need it uncompressed for the Brautenberg. And then I'm gonna initialize the Brautenberg. So this is multi-threaded, so I'm just asking for 4 threads. I could make it more. There's some point where it's actually it's not faster. I think it even gets slower if you get just too many threads for your stuff. But yeah, 4 is okay. And basically, yeah, I'm gonna init this API. I'm gonna get the circuit size because I need to, basically initialize my CRS with that. So I need to get circuit size and its subgroup size, and then init the SRS, which is the ceremony that we did that you need for your proofs. And then the AC composer is going to be using for generating the proofs. So this is pretty much copy and paste, and we are basically abstracting this away with a new library that's going to come in a few days. That's going to be abstracting this away, and so you don't even need to think about init. Just go and import that library. It's really cool. So this is the init function, and then the witness. So if you're used to ZK, you need to generate witnesses, which is basically, basically pass your inputs and generate something that you can use to prove. So this is the generate witness function. It's basically just, it expects a map. So I'm gonna, that's here when I'm lazy, because I need to pad each input into 32 bytes, and I'm too lazy, so I'm just using ethers for that. I just go and pad, because let's say that you have, your input is 1, 2, it's like 1, 2, it actually expects like 0x, then 31 zeros, and then 1, and then so, and same for again, this is something that's going to be abstracted away. For now, this is what we have. And yeah, and then finally you have like your witness map, so you're going to pass it to your ACVM and get your witness map and the buffer, because it needs to be compressed. And this will get you the witness. Now for the proof, this is the good stuff. So inner proof, I think I copied this from the wrong place, I suppose. Check. This is from the other example. Yeah. Okay. Just gonna copy the generate proof. Here, generate proof. And yeah, just gonna remove this. Kev is probably laughing right here, right now, and say, yeah, I remember that. Okay, so this is because of recursion, if you need to use this for recursion. So yeah, I'm decompressing my witness here. And I'm gonna pass it to my backend to generate my proof. And then I get my proof. It's really cool. Now, I need to verify it. I want to verify that. So I'm gonna go and verify my proof. And say, here, verify my proof. Also gonna remove this. It's kind of the same thing. You just go and verify your proof. And then finally, I need to destroy my API so it doesn't clog. So yeah, just this. Cool. So it's a very basic example, and as I say, it's going to be even simpler with the new library. Sorry, CodeLens. Cool. So hopefully this doesn't have any errors, so I can go and just run my thing here. Go browser. Oh, sorry. Browser. I'm gonna say yarn. It only has node modules, but that's okay. Yeah. And can run dev. This will, as you see, like in package.json, just goes and just runs next. There's no big deal. Oh, port is in use. Okay, that's okay. I can use 3001. Oh, can I treat properties of undefined? I don't know. Maybe I'm importing this from new Noir. Oh, here, yeah, it's expecting the circuit here. So I need to import it. Import circuit from circuits, and then targets, and then, oh, it's still called Noir start. So I'm gonna say Noir circuit. Yeah, and hopefully this will work. So it's initializing, remember that init function that I was mentioning? Yeah, it's initializing that. Actually gonna start a console here so you can see like the output. Oh, sorry. So it's initialized, so I can try that and get some error. Expression has too many unknowns. I don't even know. I'm gonna just copy the sheets. Maybe I missed something. Okay, cool. Yeah, I copied this from the wrong place. Maybe I'm gonna copy from Noir starter. It's here. Sorry, I copied from the surprise example. Yeah, this looks like it could work. If it doesn't, I'm just gonna give up. Yeah, okay, cool. So basically that's it. You see, it generated the witness, then generated the proof, and then it verified the proof. And that's it. Then the on-chain part is in Noir Star. You can go there and see that working. Cool. So now for the surprise, it's recursion basically. So what is recursion? This is all cool, but let's say that you want to verify a proof within a proof. For example, if your circuit is too big and you're gonna spend all the gas, and for example, maybe it will be worth to verify that proof within a proof. And so that's where recursion comes from. For example, you can have a game, like a turn-based game, where nothing needs to go on-chain. Because I make my turn, I make my move, I send it to the other player verifies that proof within a proof, and also generates his play, and then so back and forth. And basically have this state channel where only like the last proof needs to go on chain. That's really cool. I'm very excited about recursion. And so basically I'm just gonna show you how that works. Noir examples. Here is it. So Noir examples is another repo that the DevRel team has been putting together. So there's examples for using it with voting, recursion, and a work in progress, which is Stealth Drop, which is really cool project as well. And so here, there's the recursion. So I'm gonna basically, I have here so you don't have to. I have here the code. And basically, I'm gonna just show the circuit so you can know what I'm talking about. You see, there's this main circuit. It's very easy, the same basic x different from y example. And then I have another circuit, which is this. It's not complex. It basically says std verify proof. So I pass the verification key, which is needed to verify a proof. I also pass the proof, obviously. That's what I want to verify. I'm going to pass the public inputs for the inner proof. I'm passing the hash of that key because could be used for some backends. And then inputs aggregation object, because you're actually not, it's kind of a folding, right? So you pass the aggregation from the previous proof into this proof. So yeah, if you're like, you can use, basically this is the recursive proof. There's no need to have another one, unless you're like, for example, you can have two of them if you want to verify, for example, a Merkle tree. If you want to just recursively aggregate the hashing of a Merkle tree. And so yeah, we have this recursion. We have these two circuits, and then I'm just gonna change my Noir class to basically verify the inner proof and generate the inner proof and the outer proof. So inner proof is the one that you're the initial proof, and then outer proof is the recursive one. And so yeah, just basically the same thing. I just need to add these little API calls that basically get to verification keys and hashes them and etc. That's really cool. That's available in Ratzenberg, so you can basically get everything you need for the public inputs, and then generate the outer proof, verify the outer proof, everything, and run it. And so I ran it already. It's on port 3000. That's what was clogging port 3000. So you're gonna see that on the surface it actually looks the same thing, because it is, right? It's the same inner circuit. So there was no change in what I'm putting in here. You're gonna notice that it takes a little bit more to initialize, because you're initializing twice Ratzenberg API, so it also uses more resources, obviously. And also the proof is gonna take a little bit more to generate. And so it was very, very fast to generate the inner proof and to verify that. And then you see the console log just gets the proof, like the proof, just as the backend expects it, and verification key, and also the hash, and then it's generating the witness for recursive circuit, and creating that proof. So that's the part that takes a little bit longer, because it's the recursive circuit, and it's not simple, but hopefully. While I'm speaking still, it will work. But again, you can just pick this proof, put that on a smart contract. And so this basically allows for the most amazing use cases you can have in ZK, right? Because it's almost, you have like a constant size proof for whatever you want. And so, your circuit is too big, no problem, just split it in two. Right, and just verify those two parts. Your Merkle tree has too many levels, no problem. Just prove like two halves of the lower part of the tree, and then verify that those two halves in the recursive proof. So pretty much anything can be done with recursive proofs. So yeah, generated the proof, and now verifying the proof. This takes a little bit because of the verification key. I'm kind of taking it twice, and I shouldn't. So that's why verification is because I've done it already. So yeah, let's verify the proof. And yes, it took less than 1 minute to basically init the SRS, make the proof, load the verification key, and verify. So if you optimize this, like by storing the verification key, for example, you can make this much faster. And so, yeah, I'm very excited about recursion on Noir. Cool. And yeah, that's it. I mean, I could be here the whole day speaking about Noir because I absolutely love this language. But yeah, do you have any questions? Yes. There's a mic somewhere. I don't know who has it. No, it's not on the table. It was. Yeah. Okay. Yeah. Just speak.
I'm curious about the efficiency of the ACIR compilation versus targeting something like RISC-0 and doing the full VM. Can you speak to that and if there's been any benchmarks or any way of comparing?
I know it's kind of efficient. I mean, you saw it in the example how fast it was to generate like the witness. And so that was pretty fast. That's not what's clogging the whole process. But as for the benchmarks, no, we currently don't have benchmarks. That's something that we are working on.
I can try and field some of that. David, so we don't have apples-to-apples benchmarks, but the expectation that it's substantially faster than zero because we're not going through the VM abstraction, particularly using this architecture. It means that it's much more efficient to directly express a computation by strength than it is to compile it to 5 and copy it to 5. I think actually the way Guy is did a talk on this, or was doing a talk on this in parallel about various performances of various VMs, where effectively you always need to pay an overhead with a virtual machine, and the complexity of a virtual machine increases the scale of the overhead. Honestly, like Noir and RISC-0 have very, very different execution environments, because Noir is designed for privacy, where you're constructing your proofs locally on very resource-constrained devices. So it's worth going through the additional complexity of writing your programs directly in a language that can maximize efficiency. Whereas the zero approach is to make it as easy as possible to write circuits by basically just making it compile to your RISC. But in doing so, you need to construct your proofs on varying resource-intensive devices, usually optimized hardware, that kind of thing. So they're very, very different targets.
Thanks, Zach. Any other questions? Will it work on your phone? Yes, that's intent. But I actually tried like the basic Noir starter example, and it didn't work. So I guess I did something wrong. but yeah, it worked previously in the past. Yeah, I'm kind of saying kind of redundant. Yeah, it worked previously, and so yeah, it will work on your phone. Actually, that's one of our goals. We need to fit everything in 1 gig of RAM. Yeah, it's hard, right? Yeah, we're gonna do it. Yeah. Any other questions? Yes? Was that a question? Yeah.
What other kinds of backends do you support? I mean, do you do you support like say R1CS based backends?
Yeah, we had a version. We had ACVM for Merlin that you could use that, and R1CS, I believe. But I'm not entirely sure if it works currently because we've been making a lot of changes to the ACR as well. But we support Brasenberg, obviously. We support Halo 2, which is kind of a new, and I think it's not worth it. I mean, you get like the simplicity of Noir, but then you don't get the same speeds as just writing directly in Halo 2. And I think that's it for now. We're working with other teams to implement other backends. So if you have an idea of a backend that would be cool to support, just talk to me at the end. And yeah, it's not difficult. Basically, just need to write the ACVM, and we actually have I believe some kind of starter or boilerplate or something for the ACVM. And yeah, just need to write this translation thing. Any other questions? Cool. No questions.
Thank you, Jose.
Thank you.